frequently, and Doug said, "Hey, I got a slot, way out, a couple months out that is open. Would you be available?" And I said, "Sure." Had no idea what I was going to do a presentation on. So I do two kinds of presentations here, or other places where I've done presentations. One is where I know something about the subject. This is something I've learned about, and I can share some information, maybe help other people. Others are topics that are sound interesting, but I really don't know a lot about them. And I've learned over my career that the best way to learn about something is to try to teach it to other people. Just a second. And so, as Ken said, I'd read about this asteroid Apophis, which they thought was going to hit the Earth, and then it's not going to hit the Earth, but it's going to get real close. And then I saw some videos on YouTube about this. The end is coming. You know how the YouTube videos are. And I sent a note back to Doug, and I said, "How about if I do something on killer asteroids, or the issue about?" He said, "Go ahead." So, do any of you know the phrase "I bit off more than I could chew"? Okay, so I bit off more than I could chew on this one, because every time I started to do my research and I started to build this thing out, it became a monster all of itself. And I said, "Oh boy." So I think I agreed to do this with Doug 2 months ago. I finished it on Tuesday because there was just so much I kept finding. We could have been here until dawn and I wouldn't have covered it all. Tuesday, yesterday. I'm going to share this. Let's see if this works. Okay. Now, I did this in PowerPoint, but I'm showing this in Google Slides because I don't have PowerPoint on this computer. So we'll see how well it works.
It's looking good on Zoom, so.
Are you guys seeing this at home here? This turn up the volume thing? Yeah. Now, for the folks at home, I don't have the speaker on my computer turned on because we're getting feedback. So if there's a question, Ken will pick it up and he'll repeat it to me and I'll answer it. If you have a question, raise your hand, blurt it out. You're not going to upset me. You're not going to throw me off. I might ask you to hold it because I'm going to get to that. But please feel free to jump in. And if you have some contributing information about where I am and what I'm doing, by all means, offer it up. So killer asteroids are coming. And as I said to the folks here, I saw this image and I went, I love that image. Forbidden Planet, monsters from the id. And this is where they finally show it, show what the monster looks like. That's this talk trying to keep me from getting it together.
Did you send that out?
Because this thing became a monster. Okay. So the thing we talk about with what we concern ourselves with, I put this into the category of natural disasters. Hurricanes, tornadoes, earthquakes, and the general category of astronomical impacts. Okay? The first three are well known, but we don't have a way to stop them. All right? Let's see, can I get this thing on the side here cleared?
Click on the little minus. Yeah, there you go.
There we go. Dangerous astronomical impacts could be addressed if we know about them in time. And I want you to keep that in the back of your mind, because as we go through this, everything that we are working on and everything that we would need to do to address this, the underlying factor is time. Okay? And it'll come out as we're talking about this.
What about volcanoes? That's a natural place too, right?
Yes. And there's probably earthquakes, or not, but whatever they are, we can't stop them. That's what makes this one different. Okay? So far, we don't have any way to stop these or volcanoes. But we could stop an astronomical impact. if we work on it, there are ways to do this. All right. So what is an impact event? I want to define, I'll define terms in the beginning of this. When something and the Earth collide. Hitting the atmosphere counts as a collision. Meteorites, typically grains to about 1 meter wide. That's what we see. We go to see the meteor showers, whatever. This is what we're seeing. Thousands hit the Earth every year. Most never reach the ground. Some are a little larger, with small pieces making it to the surface. Larger impacts can cause local, regional, national, or global disasters. The location of the impact is a key factor as to how destructive these events are, and I'll address that later on. Did someone have a question, or I see a hand? No. Okay. Let's get some terms down. Meteor. This is actually the streak you see, as defined, by the astronomical people. Light crossing the sky from high-speed entry. The meteoroid is the solid object itself that's making that streak. And typically what we're seeing is something between 30 microns and a meter. We get a meter rock coming into the atmosphere, we get a fireball. Meteorite, smaller particles are considered to be interplanetary dust. And this is falling and hitting the atmosphere all the time. Meteorite is a meteoroid that reaches the ground. An asteroid is a rocky object that orbits the sun. All right. And note that the terms are often used interchangeably. So if you hear somebody talking about a meteorite, asteroid, because an asteroid, once it enters the atmosphere, actually becomes a meteoroid, a meteorite. So the terms get used loosely. We're generally talking about the same stuff, just bigger and smaller. Now, and by the way, I'm talking about asteroids, but comets would fit into this too. I just didn't want to branch out into a whole nother thing about comets. Okay, but you can put comets and asteroids into that same category of something out there that's hitting the Earth. Main belt asteroids, this is what we know around Mars. Between Mars and Jupiter is the main belt. Trojan asteroids are asteroids that actually track with planets. So there's a whole slew of them around Jupiter. There's a slew of them around Neptune. There's some around Mars. We even have one tracking us. So this is a meteor, or an asteroid rather, that's actually traveling with the Earth. Okay, and they typically hang out in the Lagrange points, where the gravity from the Earth, the gravity from the Moon, the gravity of the Sun all kind of zero out. So the asteroid, rather than orbiting the Earth or orbiting the Sun, is just riding along with us. And we know we have at least one. Composition, as we'll see later on, becomes very important, both in the damage they can cause and what we can do about them. So C-type are asteroids that are most common. It probably consists of clay and silicate rocks and are dark in appearance. They're among the most ancient objects in the solar system. S-types, stony, made up of silicate materials, and nickel iron. All right, so this is what we would think of as rocks. All right. The M-types are metallic, mostly nickel iron. Their composition is different related to how far from the sun they formed. Some experienced high temperatures after they hit. They actually melted. And just as with the Earth, the iron fell into the center, and there's a lighter surrounding on the outside. All right. Now, we do have some natural defenses from things that hit the Earth. The first is the atmosphere. We've all witnessed this as astronomical observers when we see meteor showers and stuff. Most asteroids are under 100 feet, will likely burn up in the atmosphere. The larger ones in this range can produce fireballs. And these can still produce dramatic airbursts that can cause localized but typically not catastrophic damage. We're going to talk about that more. Water. Asteroids coming at the Earth. Big nasty asteroid, mile across, oh my God, probability is it's going to hit water. Okay, 70% of the Earth is water. Almost all of that is in oceans. All right, and so if one of these things hits the oceans as opposed to hitting land, it makes a huge difference on what kind of damage it causes and how widespread it is. And again, we'll dig deeper into this later. And one of the interesting things I learned about this, I had seen this on an episode of anybody who knows the series How the Universe Works. I'm absolutely addicted to that. I think I've watched the whole series like 7 times. There was a whole episode about this subject and whether or not a large asteroid hitting the Earth would, hitting the ocean rather, would cause a tidal wave. And of course, we all know about, and again, it'll be in here later, about the one that wiped out the dinosaurs. But what they did in test labs and discovery and everything is that this thing hits in the deep ocean as opposed to the shallow shorelines. The continental shelf can actually help dissipate, say, a tsunami wave coming in. That's not to say that there won't be damage, but we're thinking these big asteroids are going to cause, like the one that the dinosaurs got a gift on. They're talking about a tsunami that covered a major portion of North America. But if it's out in the deep ocean, we have a much different response and a much reduced damage wave. So collision avoidance. Can I get rid of that top thing?
Do it, I don't remember.
Try the 3 more now, more down. Let me pull this down here. Maybe it'll be a little less distracting. Okay, collision avoidance strategies. For anybody who doesn't know, that's dodgeball over there. Because I'm thinking about, what is this really? It's like dodgeball. Something's coming at you. You're trying to get it, trying not to get hit. So collision avoidance strategies, fragmentation, scattering the fragments so they'll miss the Earth. Anybody who's seen Armageddon? Okay, we're going to send a bunch of guys up in drilling equipment. They're going to drill a hole in the asteroid and they're going to put a nuclear weapon in it. And of course, those drills are loaded with 50 caliber machine guns, fully loaded with ammunition. Why, I don't know, but it made for a very dramatic thing. And as there are so many errors in that movie, and I just love it. That's like one of my favorite movies. But anyway, fragmentation, the idea is let's blow it up, let's scatter it, let's make it smaller. Delaying or advancing the asteroid's arrival so it misses the Earth. Putting a force on this asteroid so that, because the danger is that we're here, it's here, we're going to arrive there at the same time. So if I can deflect it even to a small amount, I can potentially avoid the impact. Now, how do we do that? Well, there are direct methods such as nuclear explosives, Armageddon, or kinetic impactors, rapidly intercept the target's path. Direct methods are preferred because they are generally less costly in time and money. I'm going to build something, I'm going to shoot it into this thing, I'm going to hit it with it, and hopefully I'm going to deflect it. They're most effective against solid objects that can be directly pushed. But in the case of kinetic impactors, they're not very effective against loosely aggregated rubble piles. And we're going to talk more about that later. Indirect methods such as gravity tractors, attaching rockets or mass drivers, are much slower. They require traveling to the object, changing course, doing all sorts of stuff in order to get this to work. All right. So if we're going to get chased by something, we would prefer it be.
So I guess, Ed, we have it advanced enough that a Star Trek and shoot lasers at it, huh?
What was that, Dino?
I guess we have it advanced enough like a Star Trek, shoot lasers reflected.
Oh, right.
Well, we're actually going to get more into that later, but hold that thought, because a lot of these things, a lot of the issues that you run into and how you're going to do this stuff becomes a matter of degree, how long it takes to do it, how much you can move it. Look, the hazard by the numbers. I found this chart very, very interesting. How large is this asteroid? How often are these things likely to hit us? Now, just because it says once in 100 million years doesn't mean it couldn't hit tomorrow. Okay. How bad the approximate impact energy? So these are measured in megatons. All right. And as I point out later on in the slide set, the bomb that was dropped on Hiroshima was 15 kilotons. And we know the devastation that caused. Okay. So if you're talking about something having an impact energy of 10 megatons, you do the math. That's pretty bad. And that's only a 50-meter asteroid. You get the bigger ones. All right. How many? Millions a year. Okay. Wait a minute. I forgot the time scale on it. Oh, how many have we identified in these classes? All right. Millions. Hundreds of thousands, tens of thousands, hundreds, a few. Thank goodness. Percent discovered. This comes in later on in the presentation, but it brings in now. We've done estimations of what's out there. What do we think is actually out there? And how much of it do we think we actually have identified? So these smaller ones, we only think we've got less than 1% of them identified. Okay, but they're, less likely to be a serious problem. Here, the 50-meter, these can be pretty serious. We only think we've got less than 10% of them identified. And so on down the road. The bigger they are, the easier they are to identify. And we're going to focus in on this to a large extent as the presentation goes on. What's that? Okay. So those, by the numbers, how bad is it? Here are some examples of some actual hits. So in October of 2022, a 2-meter meteorite caused an airburst, and the largest recovered piece, about 12 inches, hit a car in Peekskill. Okay, so yes, Chicken Little sky is falling down. Chelyabinsk, Russia. We've all read about this in the news. February 2013. This was a 20 to 25 meter meteorite airburst. Over 1,000 people injured and widespread moderate property damage. Most of the damage was glass. The pressure wave that was produced by this meteorite shattered glass all over the place. And because this thing came in as a bright streak airburst, people went to the windows and go, "What's that?"
Oh, man.
Boom. That's the vast majority of the people that were injured. It was glass injuries. Okay.
Wow.
Ed, the one on Peekskill, October of 2022.
Yeah.
I get this a while ago.
It was
more than
earlier
30 or
than
40
that.
Years ago.
Maybe 2002 or something.
Oh, maybe it was 20.
Yeah.
This is what I picked up, but maybe I made a typo there.
Yeah, it's gotta be back in the 1960s or something.
No. It's more recent than that. But you know what? Let's assume I got the date wrong.
Yeah.
In my editing. But the point is somebody's car got hit.
And it became worth a lot of money selling the car. Somebody bought the car and somebody bought the meteorite.
Yeah. Tunguska. Anybody who's read anything about meteor strikes and whatever, this is a monster. This was June 1908. 160 to 200 foot wide meteorite. Now, this is big. The air burst at 3 to 6 miles altitude. Never touched the ground. Up in the sky, boom. Well, an airburst means whatever it was exploded not on the ground. It didn't explode on impact. It blew it up in the sky.
Melted. Yeah.
Flattened over 80 million trees,
Wow.
over 830 square miles. Now, when I saw that, I said, how do I conceptualize 830 square miles? 2/3 the size of Long Island.
Wow.
So if this airburst occurred over the Nassau-Suffolk border, okay, everything from Queens out to Riverhead would have been flattened. Okay, mass destruction. Explosive force estimated to be 5 to 15 megatons. Okay, as they say here, the World War II bombs were 15 to 25 kilotons. I don't know why I can't get rid of this. Hold on a second. I got to get rid of this. Give me 1 second, folks.
Peak skill was 92. I just looked it up.
Was it 92?
92.
Okay, so I
You were close.
made the boo-boo.
It was in our lifetime.
Yeah, all right. It's probably better off up here. All right. The Barringer meteor crater.
Menu.
All right, go ahead. If you can get rid of it, fine. This occurred about 50,000 years ago.
Halfway down there.
Thank you, sir. This occurred about 50,000 years ago. This was an iron core meteorite, 100 to 170 feet across, traveling, they think, about 27,000 miles an hour. Now, here's an interesting little tidbit. I don't think I've put this on any of the slides. If you took an asteroid and doubled it in size, the impact energy would double. If you doubled its speed, the impact energy is multiplied by 4. Okay, so not only do we concern ourselves with how big they are, but we concern ourselves with how fast they're moving. All right, so little tidbit. The estimated shock wave produced winds of over 1,000 miles an hour. All vegetation destroyed over a 400 square kilometer area, about the area of Nassau County. Estimated all animals would have been killed within 2.5 miles of the impact. Now, that's all. Now you go out double that far, only half. Okay, so you've got mass destruction, 100 to 170 foot rock.
So interestingly,
All
if
right,
I
and
can
here's the
interject
dinosaur
1
killer.
second. The
Estimated to have been 10 kilometers. Impact offshore near Yucatan Peninsula. 100 million megaton blast. 100 million megaton. Put the huge amounts of sulfur in the atmosphere. This, from everything I read, was a key issue on the extinction event that was caused by this. Because this hit in the shallows. It hit in the water, but it hit in the shallows. Caused a huge tsunami. This is where we're starting to talk about like North America being partially covered, if not fully covered. Huge amounts of water vapor into the sky, and a huge amount of sulfur and other minerals that completely engulfed the planet. And this was attributed to one of the major reasons why such a large extinction event happened. 70% of all species went extinct, based upon what we've dug up. So is this going to happen to us? Maybe you, not me. The dinosaurs didn't have telescopes or a space program. We do. So again, let's get into some terms here. Near Earth. Okay. Near Earth objects, asteroids and comets with orbits that bring them within 1 1/3 times the distance from the sun to the Earth, or about 1.3 astronomical units. That's how we define a near-Earth object. If it's going to pass within that area, it's a near-Earth object. Potentially hazardous objects that bring them within 4.7 million miles, 7.5 million kilometers of Earth's orbit. That's this dark blue zone. This is Earth's orbit. Size that could do regional damage should they impact Earth, about 140 meters in size. Again, I mentioned this earlier. We're going to come back to this 140 meters because there's a lot being poured into things 140 meters and larger. And just, I'm sorry, the dotted line is the orbit of Bennu, which is one of these potentially hazardous near-Earth objects. Now, time is our greatest weakness and our greatest weapon. How long does it take us to find these things? How far away are they when they find us, when we find them, and what can we do about it? So, how quickly could we respond? Estimates are that NASA would need at least 5 years of prep before a mission to intercept an asteroid could be launched. Okay, that means if we spotted it 5 years out, okay, and started the effort now, we're probably screwed. Most deflection efforts for a large object would require a year to decades of warning to prepare and carry out the mission. It falls into the simple category of the further out it is, if we're going to try and get it to avoid us as opposed to trying to destroy it, which for the most part is considered to be impractical. The further out it is, the less we have to push it in order to accomplish the task. So if it's a year out, we might need something bigger than we could possibly launch. If we find it 20 years out, we might be able to take it away with an impactor that we can actually send up. There are currently no known significant threats of impact over the next 100 years. So right now, based upon what we know, and for the most part, this is this 140 meter and larger category, we don't know of any that are likely to hit us within the next 100 years. But remember when I showed you the chart earlier, but we think we've only identified about 40% of what's out there. So more than half of what's out there, we're pretty sure we don't know it's out there. We don't know where it is and where it's going to go. There are many that will get close. Among them is the 1,100-foot wide asteroid Apophis, which will pass close to Earth in 2029, 2036, and 2068. And this is the one that led me to want to dig into this.
Yeah, that's the one we're gonna talk about. They think that in 2029, but it should be visible at the third magnitude star when it flies by. And I don't know if it would be visible from here or from other part of the world.
Yeah.
I don't know.
Actually, that's what I read, about a third magnitude star when this comes in. So let's look at this. It was discovered in 2004. Originally, we thought it was going to hit the Earth. Okay, this is a big rock. Later, it was determined that it would not hit based upon tracking. We believe that based upon current information, April 13th, 2029, it'll pass less than 20,000 miles from the Earth's surface. That's inside the orbit of many of our communication satellites. So this is what you call, oops, this is going to be real close. This is closer than, as I said, some geosynchronous satellites.
The accuracy of that projection is what?
I can't give you a percentage, but they're very confident. Okay, 2036, 2068, they also believe it's going to miss. But I'll get to a little bit about that later on, John. If I don't address accuracy on these predictions, you come back to me. If it were going to hit the Earth, could we have done anything about it? Pretty much as of today, no. So what's NASA's role in planetary defense? Because that's what we're really talking about now, planetary defense. NASA's been conducting a near-Earth object survey and research program since 1998. In 2016, they created the Planetary Defense Coordination Office. The National Academy of Science states NASA's PDCO was the critical organization to advance U.S. planetary defense capabilities and initiatives in the next decade and beyond. It'll come out a little bit as we go forward, but I want you to think a little bit about the World Trade Center. And when they hit the World Trade Center, one of the things that we learned after that disaster was that the fire department couldn't talk to the police. The police couldn't talk to FEMA. Nobody could talk to anybody to coordinate information, coordinate efforts. And so everybody did the very best they could, but they all worked alone because they didn't know how to talk to each other. So a lot of what's going to come up along here is going to be about how NASA is helping to pull this together.
And on that note, when you were talking about it coming into the geosynchronous orbit of satellites, what's the likelihood that our communication system, which so heavily depends on those satellites, will be negatively impacted?
It's hard to say. I actually don't have an answer that comes out of anything I read. But just logically, we're talking about projecting all the satellites in all their positions in 2029, and we're launching them continuously. Okay? So I don't think anybody can make any kind of a reasonable projection about the probability of something being hit. All right? And even if I read it's only a 3% chance, I wouldn't believe it, because there's just too many variables. But it is possible that this thing could take out some satellites.
That might interfere with the ground communications regardless.
I might not be able to Google my next presentation material.
I don't know if you said it, but we actually had a satellite hit an asteroid and moved it all of it. And I don't know if you mentioned that, they did that for a reason, to see if they can deflect an asteroid that does hit the Earth. And so NASA's done it. It only moved it like tiny bit.
I'll be getting to that. That's the DART project. All right, but absolutely correct point. So in April 2023, the US government released the National Preparedness Strategy and Action Plan for Near-Earth Object Hazard and Planetary Defense. This is now a defined project that the government has announced. But I want you to take notice, to address the hazard of NEO impacts over a 10-year period, primarily by helping organize and coordinate interagency NEO-related efforts. All right, again, our government, China, Japan, we've all got these little things going on. Okay, but are they working together? And we'll talk about some of the things that have been accomplished. So the strategic goals: enhance detection, tracking, and characterization. Characterization meaning how big is it, how fast is it, what's its orbit look like. Improve coordination on NEO modeling, prediction, and information integration. I have information, you have information, we put it together, and somebody else is using it. Okay? Until we started doing these projects, this wasn't happening. Develop technologies for NEO reconnaissance, deflection, and disruption. Increase NASA contributions to international cooperation. Coordinate with FEMA, okay, and other agencies to strengthen and routinely exercise NEO impact emergency procedures and action protocols. Somewhere along the line, we're going to get hit. Now, it may be a big one, it may be not so big, all right, but somewhere along the line, one of these things is going to get through. Are we prepared for it? Do we know what to do? Okay. They've actually run exercises on this. Again, how the universe works. One of my favorite series. They had a whole episode on a simulated disaster of an asteroid hitting New York City. Okay, I think it was 500 meters in size. And where it hits right in the heart of Manhattan, what would the damage be and what would they do about it? And what were they going to do to try to deflect it and all this kind of stuff? If you know the series, I think it was in season 8, if I recall. It's actually kind of interesting to see what it's all about. But that's what we're talking about here. Improve and enhance planetary defense activities, enhance NASA's strategic communications related to planetary defense. So taking that initiative, basically assessing, determining NEO population survey. This is being focused mostly in the Center for Near Earth Object Studies. This is an agency that operates today. Search, detect, and track. Down below in the lighter colors, I don't know if you can read them or not. You've got the ground and space-based observatories, Minor Planets Center, the International Asteroid Warning Network. So these are things that are already in place that are being tied together. Characterize, determine the physical characteristics of NEO's size, shape, composition. Today, associated with this is the Infrared Telescope Facility, Goldstone Solar System Radar, and NEOWISE. We're going to talk about some of these later on. Plan and coordinate, work with the U.S. interagency, collaboration on effective actions for impact threat response. We've got the Space Mission Planning and Advisory Group, Planetary Impact Emergency Response Work Group, and Planetary Defense International Work Group. By the way, if anybody's expecting me to be putting things up here about rockets going and blasting things away, that's not it. Okay, because we aren't there. And I'll go back to that again. If we were to, if Apophis was going to hit us in 2029, we probably couldn't stop it. All right. Mitigate, DART, double asteroid, redirection test, DART, FEMA exercises. In other words, what do we do to respond? So these are the basic areas that this planetary defense is built around. Oops. This I found really interesting. This was one of those things where you keep digging and you come across something and you go, geez, I need to put a slide up about that. In 2005, Congress passed a bill requiring NASA to find and track at least 90% of all near-Earth objects 140 meters or larger by 2020. Okay, NASA mandated this, but neglected to allocate any funds for the effort. It's kind of like when the state tells your school that you have to provide these things, okay, and you figure out where the money's going to come from. In 2010, the White House proposed a funding increase for NEO observations. As of January 2019, only 40% of the total estimated population of hazardous asteroids 140 meters and larger had been found. There's been a trend to transform the effort from a limited ground-based sky survey into a full-fledged planetary defense program. You saw the strategic plan that was announced in 2023. NASA's 2024 planetary defense budget is $142 million. That's $55 million more than they asked for. Okay, so someone in the government is taking this seriously. Okay, when you ask for money and they give you more than you asked for, they realize we got a problem. So first we need to know they're coming. Time is the most critical element. The sooner we know there is a threat, the better our chances of doing something about it. Large asteroids have passed very near Earth that were only detected a very short time before they passed. All right. I pick up these little news clips here and there. Says, oh, an asteroid of 200 meters is going to pass by the Earth on Wednesday. Okay, and I read further into it. They discovered it last week. Okay, all right. You're absolutely right. Last week, an asteroid of 140 feet passed within 100 yards of my house. And the only reason we saw it is because it was traveling away from the sun. And as it went away from the sun, we could see it. Some of these have passed between the Earth and the Moon. Some of those could have been major disasters. We saw them too late to do anything, even if we had the technology available. Ticking time bomb, in case it wasn't recognized what that little image is supposed to be. So where are we in this discovery process? So the way this chart reads is this is 100% of what we estimate is out there as of today, going out into the future. As of today, and then this, again, this is focused on this 140-meter or larger. All right, that means 100-meter is not on this chart, but really could do a lot of damage. So today we think we've got somewhere between 40 and 50% of these items or larger identified. If we continue with our current resources, we estimate that by 2040, we'll have identified close to 60% of them. But as I showed you earlier, we're starting to take this real serious. So predicted NEO survey completeness, combining the current capabilities with projected contribution by the Vera Rubin Observatory. Okay, Vera Rubin, I have a slide on in a minute. We think by that point we'll get to about 75%. Okay, NEO Surveyor, which I also have a slide on, after 5 years of operations, that's the top blue line, where we're getting to in excess of 90%, not necessarily 100%. Okay, so resources are being brought into the pool. Now, the Vera Rubin Observatory will be in Chile. It's an 8.4 meter mirror and the largest camera ever built for astronomy. Now, this observatory, it's important to note, was not built as a NEO facility. What it is that it lends itself very well to what we're trying to do with our NEO efforts. So as with most of these observatories, they gather data and then other people go and use that data for various purposes. It'll image the sky continuously each night on an automated cadence. The 10-year Rubin Observatory survey of space and time will image billions of objects in 6 colors. Over the course of 10-year survey, it will collect about 800 images of each location in the sky. All right. Now, why is that important? Because you have a good image of this part of the sky, and then you have another good image of this part of the sky, and you have another good image of this part of the sky. All those stars are in the same place. What's this thing moving across? It's not a dedicated planetary defense resource. The projected first light is in 2025. So it's getting very near completion.
Since there was one that was called the Synoptic,
LSST, yeah.
Yeah,
is that what this is?
Yeah.
They just changed the
the
name?
LSST. Yeah, they changed the name somewhere along the way. Okay, but I think what these agencies have discovered is if you call it the LSST, people lose interest. But if you name it after somebody important, okay, like James Webb, okay, they actually finish the project and get it into the sky. Pardon me. The NEO Surveyor mission, an orbiting infrared space telescope designed to help advance NASA's planetary defense efforts. Surveyor consists of a single scientific instrument, a 50-centimeter, nearly 20-inch diameter telescope that operates in 2 heat-sensing infrared wavelengths. It'll be capable of detecting both bright and dark asteroids. The dark ones are the really hard ones, okay, which are the most difficult to find. After launch, NEO Surveyor will carry out a 5-year baseline survey to find at least 2/3 of the near-Earth objects larger than 140 meters.
It's one dark versus light,
For the most part,
it's reflective.
it's coming toward the sun. It's coming toward us. Okay. Yeah, coming out of the sun. Yeah, Yankee dog, you die. All right. So, when things are coming at us from the sun, it's very hard for us to see them. And of course, some of these things, when they're way out there, are extremely black. They don't really reflect anything at all. They reflect, 1% of the light that's hitting them. They're like, ultra flat black paint. And so they're very hard to see. But these infrared scopes and some of the ones working outside the visual range are more sensitive to these things and have a better chance of spotting them. Estimated launch date, September 2027 to June 2028. Which is part of the reason why when you looked at that chart, and we're going out to 2040 and saying, when are we going to get to 95% of the mission, 140 meters or higher? Well, some of these things aren't online yet. Now, plotting orbits. The sooner we find the target, the more observations we can make and the more accurately we can project its path. As I said, they thought Apophis was going to hit us. But then they took more observations. And then they took more observations. And they said, oh, no, it's going to be close miss. All right, good. The influence of gravity of other objects can change orbits. If this thing is passing near Jupiter, passing near Earth, other large bodies, these are going to have an influence on that orbit. Now, we can estimate what that influence is. We can project what that influence is. But we really don't know until the event happens. This is one that I really wasn't familiar with at all, the Yarkovsky effect. So you have an asteroid. We're probably more familiar with this from the comets. Okay? As this thing is passing, coming into the sun, it will heat up. As it heats up, material will evaporate off the surface. And it actually produces a sort of a jet effect. In addition, that all those photons coming in from the sun impart momentum onto the object. Okay? So uneven heating of the surface can create a propulsion effect. Photons impact momentum. The orbit can be changed in unpredictable ways. Whether the asteroid is spinning will have an influence. If this thing's not spinning and all the pressure is on one side, it's going to be different because that side's going to get heated. This side say cool. As opposed to it's rolling, now it's more evenly heated. Well, the effect of this Yarkovsky effect may be less. One of the strategies that's just in discussion is, okay, Yarkovsky effect, we understand what this is. What if we use a paint-like material to change the color of the surface to influence the heating and resulting Yarkovsky effect? So if we want to push it, maybe we paint one side black. Okay, let it gather a lot of heat, get a greater push. Maybe that'll divert whatever it is. Okay, maybe we want the Yarkovsky effect to be less. Let's paint it white. But of course, if it's rolling, it ain't going to work. We might use space lasers that mimic this to change the asteroid's orbit. There's a D-star proposal out. And I'll mention D-star later. Now, here's one that I found very interesting. This was another one of these ones where I'm cruising along, and one of the articles I'm looking at refers to Scout. The devil is Scout. Okay, so this probably took me 4 hours to come up with these two slides. A small asteroid about 3 feet, 1 meter in size, disintegrated harmlessly over Germany on Sunday, January 21st. At 95 minutes before it impacted Earth's atmosphere, NASA's Scout Impact Hazard Assessment System, which monitors data on potential asteroid discoveries, gave advance warning as to where and when the asteroid would hit. All right? Yep. It was only discovered 3 hours before it hit. So 3 hours, we find it. Hour and a half, we were able to model it. This is the 8th time in history that a small Earth-bound asteroid has been detected while still in space before entering and disintegrating in the atmosphere. This is not something we could do before. The asteroid's impact produced a bright fireball, which is also called a bolide, which was seen from as far away as the Czech Republic and may have scattered small asteroids to the ground. Now, this is the one that I really found interesting. The asteroid that we were just talking about was first observed less than 3 hours before its impact. The early observations were reported to the Minor Planets Center. Here's where we're talking about integrating stuff. Here's an observatory that spotted something. Hey, Charlie, I found it. Oh, that's nice. Go to lunch. All right. Okay. The early observations reported to the Minor Planets Center, the internationally recognized clearinghouse for the position measurements of small solar system bodies, and automatically posted on the center's near-Earth configuration page so that other astronomers could make additional observations. All right, so you have the information, what do you do with it? Now you have a place to put it that other people know to look to make other observations. Scout, which was developed and is operated by the Center for Near-Earth Object Studies, CNEOS, at NASA's Jet Propulsion Laboratory in Southern California, automatically fetched the new data from that page, deducing the object's possible trajectory and chances of impacting the Earth. Calculated the orbit of this system calculates the orbit of every known near-Earth object to provide assessment of potential impact hazards for the Planetary Defense Coordination Office. Now, I couldn't find the date of when Scout first went into operation, but this is amazing.
That's a program that analyzes the data in real time.
Yes. I'm assuming that what it is it's a go fetch kind of thing. Something gets posted out, for lack of a better term, a web page. Scout checks that page periodically or gets a notice that something has been posted, takes it in and starts calculating. As new observations come in, Scout will pick those up and refine what it's projecting. So we say, oh yeah, 3 hours before, what good was that? But the fact of the matter is, this has only been done 8 times in history. All right, where we've seen something, projected its orbit, identified where it was going to hit, when it was going to hit, and got it right. So what are the resources that the Planetary Defense Initiative has available to it? Now, I started to build like pages and pages and pages of stuff, and I decided to condense it down. So I don't have a lot of detail on all of these things, but again, now we already talked about the Minor Planet Center, designates all minor bodies discovered in the solar system. The Center for NEO Studies, hosted by NASA's Jet Propulsion Lab. The Catalina Sky Survey, two wide sky field survey telescopes, and 1 telescope for astrometric follow-up in the Catalina Mountains of Arizona. The Panoramic Survey Telescope and Rapid Response System, and we've seen the name Pan-STARRS on some of the comets and such. 2 telescope system for wide field astronomical imaging, developing and operated by the University of Hawaii. And virtually any observatory can contribute because of this and this. All right? Because now, if you were to take your telescope and go and look and say, I think I see something nobody's ever reported. Okay, I don't know for sure, but I imagine you can probably post that. Okay, the intention is, oh, somebody found something. Everybody else go look and see if you see it too. And if so, have we known about this before? And if not, let's figure out what it's doing. Okay, because sometimes what happens is, you think it's new. Turns out we've known about that all along, but that's okay. NEO-wise, here's some of the things that are happening. A new task for an old system was launched in December of 2009 as the Wide Field Infrared Survey Explorer. This had nothing to do with planetary defense. In 2013, it was retasked to start a new mission, and the new mission name was NEO-wise. Space Telescope hunts for asteroids and comets, including those could pose a threat to the Earth. Rapidly identify and characterize near-Earth objects. As of May 2024, NASA's NEO-wise is still surveying the sky and is 90% of the way through its 21st sweep of the full sky. All right. JPL expects the mission to end early 2025 because basically the system is falling apart. Okay, it was launched in 2009. These things typically have 2, 3, 4 year, mission expectations. It completes its mission. Oh, the thing's still working. So do we continue the mission it was on, or do we retask it? And in this case, they've retasked it. OSIRIS-REx becomes OSIRIS-APEX. OSIRIS-REx, for those who may remember, was a mission to go and actually get samples off an asteroid and bring them back. So we went to Bennu, clues to whether asteroids colliding with Earth billions of years ago brought water and other key ingredients for life there. This was the original mission. This had nothing to do with planetary defense. OSIRIS-REx has now been, and by the way, they completed that mission. They got samples, they brought them back, they landed them in Utah. OSIRIS-REx retasked to become OSIRIS-APEX, a mission to study the physical changes to asteroid Apophis that will result from its rare close encounter with Earth in 2029. All right, they want to see what's going to happen to this thing as it passes by, because that could affect its orbit, whether or not it's going to be a danger to us. That year, Apophis will orbit will bring it within 20,000 miles of Earth's surface, closer to Earth than our highest altitude satellites. Earth's gravitational pull is expected to alter the asteroid's orbit, change how and how fast it spins on its axis, and possibly cause quakes and landslides that will alter its surface. OSIRIS-APEX will allow scientists on Earth to observe these changes. Additionally, the OSIRIS-APEX spacecraft will dip toward the surface of Apophis, which is considered a stony asteroid made of silicates or rock material and a mixture of metallic nickel and iron. It will fire its engines to kick up loose rocks and dust. This maneuver will give scientists a peek at the composition of the material just below the asteroid's surface. All right. So with these last two slides, the key I'm bringing here is that these things were never intended for this purpose. But we're getting serious. And so we're looking for every resource we can to say, we could use that. We could use that. Now, this is a lot of very small print, and I don't expect everybody to read it. So I'm just going to say, assessing asteroid and comet impact hazard predictions in the 21st century. So what happens is we identify an asteroid, we figure out its size, we figure out its composition, and then we characterize its orbit. It's not a hazard. We don't have to worry about that one. We'll just tag it and track it, but we're not going to give it a lot of attention. Normal zone or routine discovery, which a pass near the Earth is predicted, that poses no unusual threat. Okay, we get to two, meriting attention by astronomers, a discovery which may become routine with expanded searches of an object making a somewhat close but not highly unusual pass near the Earth. Okay, and then we have different degrees. All right, but we're going to keep a close eye on these. Threatening. A close encounter posing a serious but still uncertain threat of a regional devastation. Critical attention by astronomers is needed to determine conclusively whether or not a collision will occur. If the encounter is less than a decade away, government contingency planning may be warranted. And again, we have various degrees. And then the red zone is certain collision. A collision is certain, capable of causing localized destruction for an impact over land or possibly a tsunami close offshore. Such events occur on average between once per 50 years, and once per several thousand years. Oh, between 50 years and several thousand years. And again, we have, this goes to 10, a collision is certain, capable of causing global climatic catastrophe. So this is the way they assign weight to these things. Now we need to know the composition of these asteroids. Metallic asteroids are far more dense than rocky asteroids. You get a 140-foot asteroid made out of nickel iron. It's more dense, it's heavier, and when it hits, it's going to hit with a lot of force. And it's not going to break up. Larger potential damage, more likely to make it to the surface, well suited to impactor method to change its orbit. It's a solid item. If we bump it, that bump is going to not be absorbed, but it's going to push this thing. How much and when? That's another question. Rocky, less dense than metallic, less potential for damage than metallic, less potential. Okay, instead of destroying the entire United States, it's only going to destroy New York. Smaller, you know. If it's solid, an impactor might be used to change the orbit. And if you remember back in the earlier slides, I said, The impactor approach right now is the preferred approach and the one that we're working on most because it's the lowest cost to develop, the one we can produce the fastest, okay? And if we had to, we could probably launch one within a year or two, if we had to. USA and Japan have conducted return to Earth missions to study asteroids. And I made reference to some of that earlier. This is the one that's really tricky. Rubble piles. And you know, we didn't really realize that a lot of these things were rubble piles. So recent studies, those return missions, are part of this. Recent asteroid study missions have found that many are rubble piles that are loosely held together by gravity rather than solid bodies. Not terribly unlike that pile of stuff I have up in the right top corner. Imagine that floating along in the sky being held together simply by gravity. Harder to divert with an impactor, like shooting into a sandbag. Impactor might result in a breakup into a large number of smaller asteroids that can complicate dealing with the risk. You know, on the surface, you would say, okay, it's 1,000 feet across. If I break it up into 1,000 pieces, okay, then a lot of them are going to burn up. But yeah, but instead of hitting one site now, maybe you've got pieces hitting 12. An alternate approach might be a gravity tractor. Okay, this one always, like, I wanted to get into this, but I decided not to. Okay, basically the concept is you send a spacecraft up and park it next to the asteroid. Now the spacecrafts have mass, the asteroid has mass. Just by that fact, they both have gravitational fields, and you want to have the asteroid being pulled by the gravity tractor. Almost like a tractor beam, you know, in Star Trek. Okay. The problem with this is, in order to be effective, that spacecraft has to be very big. The effect is very small, okay, which means you need a very long time in advance to know about this, to actually move this thing. All right. If this is a year out and 1,000 feet across, parking a spacecraft next to it ain't going to do much. But if it's 50 years out, okay, this might work. And I'm just, you know, throwing those numbers as I have no validation to them.
Couldn't it possibly slowly pull it apart too?
It's possible, but unlikely. Okay, because, but you know, unlikely doesn't mean no. Because if I park the tractor here and there's a giant piece here and all the rest of it is just sand on the other side, yeah, we could separate it. But that piece that we pulled out might be the biggest threat. And all those smaller pieces that we left behind, okay, well, if we have to deal with them, I'd rather deal with that than this. But the answer is, I don't know. They've never done it. Okay, this is all theoretical. Lasers that give a gentler push by vaporizing parts that produce a gentle thrust without busting up the rubble pile. Okay. Now, as Tony mentioned earlier, the DART mission. Double asteroid redirection test. Aimed at testing the direct impact method of planetary defense against near-Earth objects. The selected target asteroid, Dimorphos, that's probably not pronounced right, is a minor planet moon of the asteroid Didymos. So you've got a big asteroid floating around out there, and it's got a little asteroid orbiting it, like a planet and its moon. There was no chance, there's no chance we weren't being threatened by this. These were not going to hit the Earth. They're well out, well away from us, so any modification we made was not likely to cause that thing to become a threat to the Earth. Launched in November 2021, the DART spacecraft successfully collided with the minor moon around the larger on 26 September 2022. The collision shortened the orbit by 32 minutes. So what we proved is that, yes, this impactor would modify the orbit of this little moon asteroid. And it was greatly in excess of the predefined success threshold of 73 seconds. So on the one hand, yep, it worked. On the other hand, what we did was well off of what we predicted we would do. So that's, maybe that's a good thing, maybe it's not. DART's success in deflecting it was due to the momentum transfer associated with the recoil of the ejected debris, which was substantially larger than that caused by the impact itself.
Can you explain that a
Sure.
little bit?
So imagine this is the surface and it's solid. All right, this is one of these iron asteroids. The impact that comes in hits, squish, imparts its momentum. All right. Now we come in and we are dropping a bomb onto land. And the bomb hits and it throws all kinds of stuff out.
Oh, wow.
So some of the energy of that bomb hitting is transferred into that material and it becomes like a thruster, right? So the impact can be likened to a vending machine hitting a football stadium, okay? The purpose of that, very funny, very interesting, is how small of a hit we produced against this little bitty asteroid. Now, I didn't record how big the little moon asteroid was. It wasn't important. This was a test to see, could we do it and what would the effect be?
I watched this live. If you were inclined, there's probably great video. It was exciting just to know what was about to happen.
Ed?
Yes, sir.
Yeah, I'm a little bit unclear, the fourth one, to take the collision shortened the motor's orbit by 32 minutes. If that means it moves slower?
It moved it closer to the major asteroid. We knocked it in, put it into a closer orbit.
Breeze also following it around.
Yeah,
Yeah, what's like 13 hours to 12.5 hours?
something like that, yeah. So it would be like if something hit the moon and moved it 50,000 miles closer to the Earth, the orbit would be faster.
But they miscalculated what it was made.
Oh, I mean, around the main asteroid.
Yes.
Oh, okay.
Now, there's a follow-up mission here. The European Space Agency has the Hera mission. Hera is a planetary defense mission under development at the European Space Agency, estimated to launch later this year. The objective is to investigate this minor moon, this binary asteroid, including the very first assessment of its internal properties. So now we hit it, we moved it, but we're really not sure what we hit. Is this thing iron? Is it rocky? Is it more rubble pile than solid? Okay, we had an impact on it, but how much do we really know about what we hit? So the purpose of this mission is to go in and understand it more. It's also to measure in great detail the outcome of NASA's DART mission kinetic impactor test. So can't tell you the details of what that means other than they're taking this all very seriously. D-Star. This is just a proposal, but basically the picture up in the right-hand corner expresses it best. It's a directed energy system for targeting of asteroids and exploration. Got to find a way to make an acronym out of this thing. Phased array laser technology for planetary defense. It's also got some nice military applications, which is probably more
Sounds
where
like
it's targeted.
Star Wars.
No, this
The
is kind
Star
of
Wars program.
no. This is I'd like you to help me build this thing for planetary defense, and the Defense Department's going, yeah, build that because we want it. It's proposed to be a standoff Earth orbiting system capable of vaporizing the surface of asteroids as a futuristic but feasible approach to impact risk mitigation. All right. The proposed system would be to raise the surface temperature to greater than 3,000 Kelvin. Engagement distance required for successful diversion depends on the asteroid's mass, composition, and approach velocity. Distance of focus and desired surface spot temperature then determine laser array size. Volatile laden objects, 100-meter wide, approaching at 5 kilometers per second, could be diverted by engaging at 0.05 astronomical units. That's pretty close, requiring an array of 100 meters on its side. So you're going, hey, we could divert this thing when it's fairly close. Yeah, but you need something big, mama laser, to do it. Oh, okay.
And imagine the energy required to power
Yeah.
a laser strong enough.
It reminds me of there was a Star Trek episode where they land on a planet and it turns out the planet's got an automatic asteroid defense system and it starts shooting at the starship. And they're thinking they're being attacked, and they discover later on that this is pushing asteroids away from the planet. Nuclear deflection. Ah, nukes. No, we don't land and drill and put a bomb inside the asteroid.
You're not fun.
Yeah, I know. Would have made a fun movie. I was going to put a video in here of Bruce Willis on the planet hitting the button. And then and miraculously, when he blows it up, it goes into this nice, two groups that go completely past the Earth.
Yeah.
Wow, that's cool. Forget about it. Detonated above the surface, it would vaporize part of the surface. So realistically, we're not going to bomb the thing. We're going to do basically a sky blast over it to try to do a vaporization to create that thrust effect. And that's how we're going to move it. So we're going to hit it with pressure wave, we're going to vaporize some of the surface, and hopefully that's the way you move it. There are many political and radioactive byproduct concerns. Yes, let's build a way to put nukes in space. Okay, and the Department of Defense of all nations are going, yeah, let's build that, let's build that.
And what do you end up with in a launch failure?
I would be willing to bet that that's being built already by somebody, probably us, probably the Russians. And kind of like what happens in these movies where, oh, the asteroid's going to come in and all of a sudden it comes out of the woodwork. And oh, yeah, well, why don't we fire a nuke at it? Well, how are you going to do that? Well, it's sitting over here in the closet, I know we signed a treaty not to build it, but, oh, thank goodness you did. Now, using Apophis as an example of time and deflection. Now, this gets into some serious math, which I didn't do. But the net effect of the numbers can be of interest. It's been estimated that a velocity change of 0.35 meters per second, where the number divided by t, where the number of years upon potential impact is needed to successfully deflect the body. Net, the sooner you spot it, the less energy you need to move it. For a large number of years before impact, much smaller velocity changes are needed. For example, it was originally estimated that there was a high chance of Apophis swinging by Earth in 2029 with a non-zero probability of returning on an impact trajectory in 2036 and 2068. Now, we have since estimated that those are not going to be impact dates either, but again, things can change. It was then determined that a deflection from this potential return trajectory several years before the swing by could be achieved with a velocity change on the order of 10 to the minus 6 meters per second. So we don't have to move this thing a whole lot, okay? But we're looking to either slow it down or speed it up or give it a little push and sort of take it and aim it over here so that as the Earth comes by, instead of hitting, it misses. By the way, for those who are asleep, wake them up in a couple of moments because I'm almost done. International collaboration. Thank you for not snoring. International collaboration. Agencies around the world are being pulled together. NASA, ESA, Roscosmos, this is China, Japan, are the major ones who are collaborating on this. And I always find this interesting because on one hand, the Russians are our enemy, and we're always trying to figure out how to blow them up. On the other hand, we're working together on the International Space Station and on planetary defense. So when that thing is hitting and it's going to affect all of us, somehow we will find a way to bury our differences, at least for a little while, and then we go back and shoot at each other again. These are some international initiatives: the International Asteroid Warning Network, Space Mission Planning Advisory Group. This is the last slide. The dinosaurs didn't have telescopes or a space program. We do. but can we be ready in time? So that ends my presentation.